The next topic that we need to cover is the Thevenin and the Norton equivalent circuit. But before we start to talk about the Thevenin in particular, uh, we need to know two concepts in advance. It's the short circuit and open circuit. At the I think, very first session or second session of the class, I mentioned them very briefly. If you go back to your notes, you might see it. But here I'm going to talk about it a little bit again. I'm going to talk about it again because we're going to use them when we start to talk about the Thevenin. So first, I start about the short circuit. So assume I have whatever I have here doesn't matter. So I have the wire coming here, and then it goes to resistance, and it goes back. And wherever it goes, so we are not right now worried. Assume the next of the circuit is here, and I don't want to draw them. So assuming this is one part of that I have. And then in this resistance that I have, so and there is a current of assuming the I goes there. Now if I look at this here, I go ahead and add another wire. How? Assume that I come here, I add a wire from here, come back down here and here. So basically, if I connect these two ends of the resistance to each other, see what happens. This is what I have. This connection, if I come and if I do that, what's happening is that basically the voltage becomes zero across that resistance. And then because the voltage becomes zero, there's no current goes through that resistance anymore. So the entire I will go here, and I through this current, it becomes zero. So nothing goes through this. So if I do that, what is happening is that if I add the wire around that circuit, around that resistance, it causes that the entire current goes through that shortcut, and nothing goes through that resistance. This is the very first condition that we have. Remember that when we have the short circuit and the voltage is the difference between the two ends, the voltage inside in this one, the entire wire is going to be zero. So we have the I, and the voltage here, voltage in this current is going to be zero in entire current, this wire. This case is called a short circuit condition. So in other words, if I have, this is a simple word, the important part is that if I have the resistance and then I connect two ends of that resistance with a single of wire, then no current goes through that resistance anymore. All the currents bypass the resistance through this connected wire. That's the important part that I need you to remember. So when later on in the Thevenin, I would say that we short circuit the circuit. When we said we short circuit this part, it means that we bypass that resistance. It's like that resistance is not there anymore. You can't assume this resistance is not there anymore. So you can't say that I can assume this is like that. So it's like that. So I have this one here, this one here. The resistance is not there, and then I have the wire goes around that. Is exactly like that. So these two are like that. So the resistance is not there anymore because there's no current goes through that. It's like that. You don't have it. You just remove it from that location. When you're analyzing the circuit, you don't need to consider it anymore. And the reason is that because no current go through that, and so also the voltage in that is gonna be zero. Why is that? And you have the voltage in this one, voltage. So we know the IR, the I goes through the resistance is zero, and you know the voltage is I R times the magnitude of the resistance, whatever it is. And we know the IR is zero, we know the current is zero, so therefore the voltage in the resistance becomes zero as well. So the voltage in the resistance is zero, the current in the resistance is zero, so it's like it's not there. So simply remove it from the circuit like that, as I have here. So if I, again, if I write, this is point E and this is point F, it's going to be like that. So it's going to be point E, and it's going to be point F, and the entire current goes from here, then goes to here, and then goes back. So it's a short circuit that we have. This is the first condition that I want you to remember. The second condition, so it's a short circuit. The second condition is the open circuit, and see what happened. Again, assume that I have the resistance like that here, and there's the rest of the circuit is here, and we don't care about that. But assume we have this resistance here, and then we go ahead so it's going to be R, and then we have also the I goes through that here. You know the I goes here. Now I'm gonna connect them with two single wire, but these two single wire are not connected, and so it's going to be something like that. So it's a two single wire, but they are not connected. It's not connected. It's not like here is this. If I have something like that, what's happening is that all the current goes here because it cannot go there, has to go through the resistance. So all the I goes there, and then eventually the entire I goes here. And because of that, whatever the I goes there, then I'm gonna have the voltage in that resistance, the V in the resistance is gonna be I times R. And then I know that because the current goes in this direction, current always goes from the positive to negative. So it's going to be positive here, it's going to be negative here, and this is going to be VR. If we have this condition and look at here, this end is connected to the positive sign directly. So if this is positive, this one is going to be also positive, because this is directly connected to that positive. Here is the negative is directly connected to the negative polarity, so this one is going to be negative. Now, because it's connected to two end of the resistance, whatever voltage the resistance have, also I'm going to have it here, because this point is connected with the wire here is like this point and this point are the same. This point and this point are the same. So whatever voltage I have across the resistance, I have the same voltage across these 2 points. So if I have VR here, I have VR as well here. Basically the wire, if you remember, I said if you have the wire doesn't do anything. You can't actually put this node here and put this node here, because this node and this node behave the same way. This node and this node behave the same way. Okay, and then the only thing, so the voltage across these two are the same as the voltage here, and the current here is going to be 0. So here there no current goes through that, and this is the open. This is what we call it, the open circuit condition. So when we go next into the Thevenin one, we use both these concepts once we use the short circuit like that, which when we say the short circuit, when we say we short circuit that resistance means that get rid of that resistance. If that resistance is like it's not there. And when we said we open circuit that resistance, it means that whatever voltage you have here is the same as the voltage of the resistance in this case. In this case, all the current goes across the resistance, nothing goes through the resistance. In this case, all the current goes through the resistance, nothing goes across the open circuit.